Okay, let's get started. So we warmed up for long enough in the first part of today. And what we'll do now is try and get a little more real. So we're going to talk about higher group symmetry or higher flavor symmetry in the standard model. So first, I think for this audience, we have to write down what the standard model is. Okay, so let's do it. So what is the gauge group of the standard model? Does anybody know? We'll talk about that. What's the gauge group of the standard model? U1. Is that? Do we really know that? Was there some fine print on what was just said? Yes. There's some interesting fine print, right? Which this audience would probably find interesting. So we know that locally, it's the Lie algebra is SU3 times SU2 times U1. But we also know that the matter content is consistent with various different global forms: a Z6 quotient, a Z3 quotient, a Z2 quotient, or no quotient. How do you tell the difference between them?
Line operator.
Okay, but don't talk to me about line operators. I'm a simple experimentalist. How will I tell the difference between them? Fractional charges. Good. Yeah. One way to falsify the existence, say, of the Z6 quotient would be to find a particle that's not compatible with it. So that you could do. So there are.
Can you explain, like, for some older people who haven't been following this discussion, although very familiar with the standard model, what do you mean by these quotients?
Oh, okay, yeah, great. So there's a question about, maybe let's, as an aside, we'll talk about gauge theory with gauge group SUN versus, say, SUN mod ZN. There are two different gauge groups with the same Lie algebra. So at the level of like the weakly coupled particle content, you don't notice the difference. Same spectrum of gauge bosons, but they have different one-form symmetries. That's the first thing. So so this one, if let's just talk about this gauge theory without any matter for a moment, has a Zn electric one-form symmetry, and the charged objects are Wilson lines. And on this side, you have a magnetic Zn one-form symmetry. And the charged objects are 't Hooft lines. So there is a magnetic monopole that you can define in this gauge theory, which has a conserved charge mod n that is not present over here. Okay, so that's at the spectrum of line operators. You might ask, like, another kind of practical point of view, you might say, are partition functions different? And they are. One way they're not different in perturbation theory, but they are different non-perturbatively. The allowed instantons in the two cases are different. So the set of bundles, right here you sum over SUN bundles, which are labeled only by a second Chern class. And here you have more bundles. You have a second Chern class and an analog of the second Stiefel-Whitney class that you also have to sum over. Yeah, so that's kind of pragmatically how to think about the quotient. Anyway, so I was just teasing you in a sense that SU3, SU2, U1, we have different possible global forms. And it's interesting to try to think about how to disentangle that. But I'm for the most part, going to ignore that today. Okay, so then this is the gauge algebra, and then I'll highlight a couple global symmetries, U1 baryon and U1 lepton. Okay, and now we're going to have some fields. Let's see if we can make this giant table. OK, so we'll start writing the fermions. There's Qi. So I will go from 1 to 3. That will be a generation index in what I'm writing. So they're a triplet, these quarks, a doublet under the weak force, and carry hypercharge +1. So once and for all, I will illustrate that I'm not a true phenomenologist by normalizing U1y to have integer charges so that we don't all get confused about 1/6 and 2/6 and so anyway. That's probably a sacrilegious thing to do in some communities, but here choosing the minimal thing to have charge 1 seems like a good idea. OK, then we've got U bar. If I leave it blank, it means it's uncharged. The down type quarks. So that's it for the baryons. Now we start doing leptons. So those are not charged under color, -3 under hypercharge, and of course they carry lepton number. The electron +6, -1. And usually you would stop here, but I'm going to add, for funsies, a couple other entries, which we may see in a moment. So I'll add Ni. This will be a right-handed neutrino. We don't know whether such a thing exists. But if it did, those would be its quantum numbers. And then I'll add H, which is the Higgs scalar. Good. And my convention is that all fermions are left-handed and vile, of course. OK. So we keep this sacred up there for the rest of the talk. And we can maybe refer to it if we forget. OK, so classical symmetry. Let's talk about the zero form symmetry to start. So I mentioned that the matter comes in ng equals 3 generations. So if we just discuss the symmetries, classical symmetries of those multiplets, not taking into account any other interactions, but just those multiplets and their gauge interactions, then, so without the Yukawas, we just have a U3 for each species. OK. That's, of course, without the Yukawas. Now, the Yukawas, we're going to include some interactions. So what are the Yukawa interactions that we know about? So there are various 3×3 matrices. There's an up type one that I'll call YU, which couples to H star in the conventions that I wrote. And then QI U bar J. There's a down type Yukawa matrix, which couples to H. And then there's the lepton Yukawa. So those are the Yukawa interactions in the standard model. OK. And these already at the classical level break most of these symmetries. And these are pretty generic matrices. They don't seem to have very obvious patterns. So they break symmetry. To what, classically? To the following: U1, L1, U1, L2, U1, L3, U1, B mod Z3. So these Li's are lepton number for each generation separately. And B is the baryon number. So again, I'm just discussing classical symmetries for the moment. Yes?
I'm confused. You don't put the right-hand part of the board?
I put U bar.
Yeah, but there is left and right chord.
No, all the fundamental fields could be defined to be left-handed with these quantum numbers.
So of each of them you have several. In the first class there are two fields.
The first class is a SU2.
The second class there are two fields.
Yeah, it's a Weyl fermion, if that's what you mean. There's Q and U bar.
Representation, not is a direct particle, quark, not a Majorana.
They're all Weyl fermions in the standard model. They're all Weyl fermions in the standard model. At the fundamental level, they're all Weyl fermions. Are you talking about after electroweak symmetry breaking?
No, in QCD.
Yes, in QCD, that's after electroweak symmetry breaking.
It is inside Q.
Yeah, because we have this doublet. Yeah. Okay. Good. So this is the symmetry at the classical level, at least. And now there's also a magnetic one-form symmetry. From this dynamical gauge field, U1y. Right? There are no magnetically charged dynamical particles in the standard model. There are electric charges under U1y with minimal quantum. So there's no electric one-form symmetry. But there is a magnetic one-form symmetry, a continuous one.
Clay? So you choose to diagonalize YE, is that? Or lambda, I don't know if that's a Y or lambda. Is that why you have the lepton?
Yeah. It's because I can do changes of basis here, and here I only have one matrix on the, but here I have two. That's why I don't end up with Bi, but I do end up with Li.
No neutrino mass in your.
Okay, whether you not to call so it's a good question. I mean, by now we know that neutrinos have mass. So you could ask, with this matter content, how do you write the neutrino mass? Well, you can write it with the right-handed neutrino or with the Weinberg operator, the Majorana mass. I'm ignoring it for right now.
U1b is a global symmetry, right?
U1b is a global symmetry, and U1L is also a global symmetry. Actually, U1b is anomalous. There's a non-trivial anomaly. The only non-anomalous global symmetry is U1b minus L. But it's conventional to list U1b and U1L to keep track of the particles.
So U1b minus L is coupled gauge field, U1 gauge field, dynamically.
No, not necessarily. Not in the standard model.
But yeah, but which one? So U1y.
U1y, yeah.
Y is some combination.
No, Y is not a combination. Y is his own guy. It's the hypercharge, right? Some extensions of the standard model consider B minus L to be gauged, but as far as what we know so far, B minus L could be a global symmetry, could be gauged.
But Clay, U1b minus L still suffer from gravitational anomaly.
It has a gravitational anomaly, yeah. Yeah, we're on the same page, yeah.
But also the discrete subgroup of B plus L can also be anomaly free. and we'll get there.
Well, okay. Okay, very good. Okay, so Juven is in the audience, so he's going to hold my feet to the fire. This is good. Okay, the idea here, of the rest of this talk is let's look at the higher group symmetry, in this case 2 group. When these Yukawas go to 0. So this will be somewhat analogous to what we did in the first lecture, though more complicated because our matter content is more complicated. And we'd like to see, first of all, is there a non-trivial 2 group in that limit? What does it say about possible UV completions? Is it a good organizing principle? That's going to be our working analysis. And of course, so here for the 0 form symmetry, I'll take G0 to be these product of the SU3Is. So I'm going to ignore the U1 factors just for simplicity. The U1 factors all suffer from ABJ anomalies, so whereas these SU3 factors do not. Okay, so just a second. So because we're working in this approximate symmetry case that is valid, thinking of this logic is going to be valid when we view y as a small parameter, we'll have to keep in mind these kind of loopholes to the emergence theorem or these various different scenarios of the emergence theorem that we talked about last time. So we'll come back to that. So keep that in the back of your mind. Yeah, question.
Well, these you call it, these are the things that give mass to the fermions.
Yes. So when H develops an expectation value, then those look like mass terms. Yep.
Is there any reason there's no U1 for the right-handed neutrino? Or we just don't?
Global symmetry, you mean? Yes. Yeah, I'm just not keeping track of it. I just want to for the global symmetry, I just want to highlight these particular parts. Yeah. Yeah.
I mean, as you said, there are normally 3 U1s, but do these just not have the 2-group diagram, or?
There are very few ABJ anomaly-free U1s. Okay. That's kind of what Juven was just telling us about.
But the ones that are normally free, do they not have the 2-group diagram? Or?
It depends on which one in particular. Okay. Yeah, it's yeah. But we'll see that we get something interesting just from looking at this SU3 structure. So, some interesting, make contact with some old physics. Yeah.
Your I in the SU3 isn't flavor, right? It's like QUD.
Yeah, exactly. It's QUD. It's just I'm looking at the SU3 factors of that big product of U's. More questions? Okay. Very good then. Okay, so we're going to compute 2 group structure constants. From triangles. So let me compute one for you. Let's look at SU3Q. Okay. So we should examine a triangle where one leg is the field strength of the U1 hypercharge. And then we have this SU3 current for this symmetry at the other 2 legs. So what is the kappa? We're just supposed to sum over the charges. So this SU3Q acts only on Q. So it's a pretty easy, we just have to take into account the charges of Q, nobody else. Okay, so we've got whatever its hypercharge is. And then we've got how many there are. SU3 color and SU3 and SU2 lepton just tell us how many copies there are. So there's 6 copies of this field. And then we have to do C2 of this is the rep that it's in under SU3 Q, which is a fundamental, right? Because we get the square here from that current. Okay, so we normalize that to be 1 in this convention. And Qy was 1 for this field, so this is 6. Okay, even I can do this algebra live. So that's how you do it. And so now you go through and you do each of these. So let's make a little list. And then we write so this is some SU3. OK, so we just did Q, and we found it was plus 6. The other ones you similarly do. U, you find minus 12. D, you find 6. L, you find minus 6. And E, you find 6. So these are some basic numbers that are there in the standard model. Questions on how to do these calculations? OK, so we immediately conclude from this that each species flavor symmetry SU3I is in a non-trivial 2 group. That's what the fact that these kappas are non-zero means. And now we're going to apply that statement. Okay? So we're going to apply that statement using the emergence theorem that we talked about last lecture. What kind of physics can you mine out of this? Well, we can constrain grand unified theories. So we're going to study the emergence theorem and guts. Given this information. OK, so first we have to say what a gut is. So the gut is our name for our UV model. So we have an RG flow starting at this gut and terminating at the standard model. So what's a gut? So I claim that a gut, for this purpose, will be a model where U1, 1 is broken. Now, of course, that's what we want to do to apply the emergence theorem. But why does it agree with our standard idea, kind of old school idea of a grand unified model? Well, what was a grand unified model? So in the original incarnation, it's a way of putting all the gauge groups into one big gauge group, right? So for instance, U1y, SU2, and SU3 go into SU5. Okay? Here, we're adopting, this includes that. Remember, I showed you that you can break the magnetic one-form symmetry by putting U1y into a non-abelian UV group. So we're keeping the same definition, but it's even more open-minded. We just want, from this point of view, an embedding of U1y into a non-abelian group. OK, so what can we say already? So let me apply this emergence theorem. And I'm going to say, without first adding matter, we'll come back to this possibility. So let's first imply without adding matter, see what it implies without adding matter suppressed by y. So what it tells us is that every gut, where we adopt that very loose definition of gut, every gut necessarily breaks each SU3I individually. And that is rather surprising. We didn't put much in, but we got this fact out. It's a constraint on how standard model fermions unify into multiplets. That's what it was in our toy model, is a constraint on, what patterns of multiplets are possible in the UV. This is a constraint on that. So to make that a little more explicit, suppose the UV gauge group is something very general, G1 times G2 times GL. And these are each non-abelian, and U1Y is somehow inside this product. That's a gut in my definition. Okay, it's not a single group, but U1Y is emergent. Okay. And then we could imagine a possible unification pattern where Q goes into some rep R1. And so Q goes into some fermion rho 1, which is in a rep R1 of that big group, etc., down to rho 5, which is some fermion that we could say contains E bar, and this is in a rep R5. If we could do that, we would contradict the emergence theorem. So that's actually excluded, right? Because in this kind of model, each rho I has separate flavor symmetry. So this is not allowed. So no matter how clever you are with group theory, you will never find any G and any reps R1 through R5 that can achieve that. Yeah?
Crucial there is the fact that U1 is broken, right?
Yes. Yes.
Isn't this kind of already why a gut model has this feature, or you're just defining that feature?
I think that's a very expansive definition of what we meant by gut. It's a UV completion, if you like, right? I mean, one of the reasons for considering guts is that the U1Y part of the standard model is not UV complete. And there's a chance of UV completing it in QFT by putting it into a non-abelian group. I'm trying to be more open-minded than saying it has to go into a simple group. Yeah. Yeah.
It's the quantization of charge, one of the original motivation to embed U1 into a.
Yeah, that's another reason is to try to explain the pattern of hypercharges. Yeah. Yeah.
Wait, but I saw the hypercharge can still be quantized without embedded non-abelian.
Well, I think the question in a more modern language, San's question is whether the gauge group of hypercharge is R or U1. We don't actually know.
wonder whether SO10, SO5 is excluded by your argument.
It is not. I'll show you. I'll show you how it is compatible. Yeah. Thank you. Of course. Yeah. So now the thing is to, of course, check how do standard guts, how do they get work into this theorem. So I'll do that momentarily. Yeah, Max.
Excluded is that this 5 SO3 cannot be independently.
Yeah, that's right. Yeah. Yeah. Yeah, Max.
Seems like the construction you're doing some kind of weakly coupled construction.
Yes, I'm doing something weakly coupled.
From the UV to the IR, where you can kind of really. But this, anomalies they typically use to make strong coupling arguments. So seems like this kind of thing should be just following from some kind of simple group theory, not from some quantum.
Well, yeah, you can probably argue it that way too. I mean, this is I'm not trying. I'm just trying to give an example where this kind of symmetry-based reasoning leads to a very general conclusion. Yeah. But yeah, we can talk about more. More questions. Yeah.
Follow-up comment. I saw that earlier, since you are motivated by this argument, try to embed the standard model group to some non-abelian group, so you try to have some kind of a sympathy freedom at UV, right?
Not necessarily. I didn't say that doesn't really matter for this kind of argument. I mean, again, it depends on what motivation you have. Like, I think originally people wanted to quantize charge. Maybe they want something asymptotically free. Maybe they want many things all at once. Here, we just keep an open mind, and I'm just talking about if you break that U1y, that magnetic one-form symmetry, then this is going to happen. Now, let me show you how it works in examples. Okay, so the conclusion you're supposed to draw is that in a gut, standard model fermions must combine. Into multiplets, so that the flavor symmetry gets reduced. Now, let's try to be more specific and see which kinds of combinations are possible. So we're going to examine the diagonal combinations with vanishing kappa. Right? Just as in our toy model, we had these two SUNs, but the SUN diagonal had vanishing kappa and therefore could be preserved. We do the same thing, but for these SU3s. Okay? So I'll arrange it this way to say what kind of diagonals are there. So we'll arrange it like this. Okay, so if you look at a flavor symmetry, an SU3 that acts on only one species, say Q, U, etc., there's nothing with vanishing net kappa. That's what this table tells us, that each of them individually has kappa non-zero. Now we could look at diagonals which act on two fermions simultaneously. And there are various possibilities. You're just trying to add those up to get 0. So you can have L with Q. That's one possibility. You can have L with D bar. That's one possibility. L with E bar. Okay. Similarly, if we look at diagonals which act on 3 species simultaneously, we again add up the coefficients.
So why not QD bar?
Q D bar, that's, sorry, this, These are the same. I should have given them. This is U bar, D bar, and E bar. Sorry about that.
What do you mean?
No, you have to flavor symmetry that acts on the left-handed vial fermions.
Oh, okay.
Yeah, so you can't change the sign on them. Yeah. This is why I insisted on putting everything in left-handed vial fermions so that I don't get confused about that kind of thing. Was there another question? Maybe I should keep writing this table. OK. U bar, D bar, E bar, U bar, E bar, Q, and U bar, D bar, Q. Four, there are none. And finally, there's, of course, one that acts on everybody. Q, U bar, D bar, L, E bar. So you should think that this table tells you what are the fermions that have to be grouped into multiplets in any gut. Obviously, you can't select all of them simultaneously. You have to select a consistent subset. But this gives you the a priori restrictions. OK, so you can have the flavor symmetry combinations on the right. OK, so the next thing we should do is, I guess, address Xiaogang's question. So let's talk about familiar guts and see that this is really realized. So this is the right organizing principle. I was unfortunately born a few decades too late to apply this in real time to Georgi and Glashow. But in hindsight, we can look at it. And for those of you who haven't studied guts, I'll do the group theory on the way for you. So you might learn a little group theory if you haven't seen it before. It's a good thing to know about. OK, so first one, Georgi Glashow. That's the gauge group SU5. How does it contain the standard model? Well, this one is kind of easy. Just, you have SU3 color and SU2, which is the standard model, embedded in kind of an obvious way in SU5. And then a diagonal generator is U1Y. Now, that decomposition tells you that the 5 of SU5, if you Higgs to the standard model, decomposes to 3, 1 plus 1, 2. Right, that's what the virtue of writing this matrix tells. It tells you how the representations are going to decompose. And then we can write the 5 bar. So 5 bar, therefore, goes to 3 bar 1. I'm not writing the U1Y quantum numbers. I'm just writing SU3 and SU2. And 10, what is 10? What's the 10 of SU5 in terms of the 5? Can anybody do group theory?
Okay, so it's 4 divided by 2.
No, not you. Someone other than Juvin and Xiaogang, maybe. What's the 10 of SU5? What representation is that? Antisymmetric, yeah. So it's the wedge square of 5, if you like, antisymmetric 2-index tensor. So this goes to the so we do the antisymmetric on this decomposition. Oh, sorry, I forgot to say that this 5 bar decomposition rule, we're supposed to recognize that this is LD bar. Right, so if we look at those quantum numbers that I left up there for you to see, we can recognize the 5 bar as having the right quantum numbers to be this. Now we do the wedge squared on this. So we got the antisymmetric part of that. 3 wedge 3 in SU3, that's 3 bar. Here we've got 2 wedge 2 in SU2, that's a singlet. And then we've got 1 cross term. So that's that. And we recognize that as U bar, E bar, and Q. So what's the UV flavor symmetry of the SU5 gut, where we've turned off the Yukawa couplings? Well, you have to rotate you have the matter in 5 bars and 10s, and you have to rotate them as full multiplets. So you have a flavor symmetry that is an SU3 acting on this, which is indeed one of our allowed entries here. And you have another flavor symmetry, which is an SU3 acting on this, which is another of our allowed entries here. People see how that works? Maybe?
They got lucky.
I don't know if they got lucky. I mean, it's when you have a correct argument, it'll work in every example. So like it's more just the examples are fun to illustrate the mechanism.
It either works or you're going to get extra matter since they just fit everything. Since if you manage somehow to fit everything, then it means that you're going to be in business.
Sorry, I didn't understand.
No, I'm just saying that they didn't have to do this check because they just see, okay, we fit everything, there's no extra matter, so we are in business.
Yeah, that's right. Yeah, that's true. Yeah. Yeah, there's no extra chiral matter, so yeah. That's fair. Okay, let's do another one, and maybe I'll do some more group theory.
Okay, since you are going to erase this level, can you summarize what's the conclusion for this level, the two-group structure?
Well, it means that if I look at any of the individual SU3i's rotating this, then each of them is in a non-trivial 2 group with U1y. But various diagonals are not. Right? There's only one U1 magnetic symmetry in the problem. So various diagonal combinations will not be in this higher group.
This SU3 is the family?
Yeah, it's the SU3 that rotates the 3 quarks or the 3 U bars, etc.
But that's not quite it's approximate global symmetry.
Yeah. I'm in the, I don't know if you were here in the morning, but we talked about, yeah, okay. Yeah.
In the QED example, you could do the diagonal, but also the anti-diagonal. That's also has vanishing kappa. Can you do that here?
Yeah, I think so, because the C2, it's just the fact that the C2 doesn't care whether this is a fundamental or anti-fundamental.
So there are more options than this, or?
No, I mean it would still act on these in the same in one multiplet.
But you need different UV completions.
Various different UV completions. I should say that if you make a list of all the possibilities that you can get, not all of them have known gut realizations. So it's not clear whether we missed some other constraints or there are some kind of other guts out there that might be low-hanging that people didn't think about yet.
Here's a possibility to contribute to history.
As opposed to just reflect on history? Yeah. Okay, well, let's continue reflecting on history for a few minutes.
But I have a comment about this. It's like it looks like history can go certain direction, which probably should be done like maybe 40 years ago, but that's not the way history evolved. I think Cleo's trying to lead the way, maybe go to some...
I'm a branch in history. I should have been inserted decades ago. I'll work on that. Okay, SO10. I'm going to do a couple more guts. A couple more famous ones. Okay. SO10 contains SU5. This is the easiest way to think about the Higgsing. So how do you restrict SO2n to SUN? What's the data you need? This is a math question, so people should know this one.
Do you mean the algebra here? Or Lie group?
I'm just talking about Lie algebras, and Juven, you're not allowed to answer my questions. So there's a nice SUN subgroup of SO2n in general. How do you do the Higgsing? What's the data that you need to respect to reduce SO2n to SUN? SO2n is rotations of a vector space with 2n dimensions with a metric, right? SUN is when you have a complex metric. So you can split, pick a complex structure. So you split the 2n dimensional vector to its holomorphic and anti-holomorphic parts. Okay. So that tells us what that is supposed to be in general. Now, to do the group theory for the SO10 gut, we need to know how a spinor decomposes. So what about spinor representations? So the chiral spinor has dimension what? What's the dimension of the chiral spinor of SO2n? In our day, people had this in their blood, right, Ellie? Everybody was working on supersymmetry, right?
Has to be 2 to some power.
Has to be 2 to some power, OK.
2 to the floor of n halves or something?
2 to the floor of n halves is the. Why don't you check it in a basic example before you. 2 to some power. Let's see if anybody can repeat the power. That's not Ellie or Juven.
For the chiral spinor is 2-dimensional, right? So it should be n minus 1 over 2. Oh, sorry, n over 2 minus 1.
So n minus 1.
N minus 1. That's for SO4. Right? OK, good. All right, we'll get a little more sophisticated. How does the chiral spinor of SO2n split when you restrict it to SUN? Everybody reading the Wikipedia article? OK, I guess I better do it.
Exterior algebra of the fundamental.
There you go. Yeah, thank you. Yes, exterior algebra of the fundamental. That's right. So you break the Clifford algebra into complex combinations, n of them, n raising and n lowering. And the n raising operators are in the fundamental of SUN. And then you act on the Clifford vacuum and generate the whole Dirac representation. That's right. And so the Dirac spinor is, if you like, 1 plus n plus 1. Now, the chiral spinor is half of that. It's every other term. OK, so now that we've had the reminder, or maybe in some cases not a reminder, of spinors and some group theory, let's apply to SO10. So we're interested in the chiral spinor which is dimension 16. And it will go to 1 plus I skip the next term. Then I skip the next term. And then I'm done because of dimensional reasons. Which is what under SU5? This is 1. Who's that? 10. Good. Yeah, that's the antisymmetric tensor on 2 indices. Who's that? Say it loud. Yeah. 5 bar. OK, 1 plus 10 plus 5 bar. And this is everybody. This is Q, U. It's everybody and a friendly singlet, which was that right-handed neutrino that I wrote up there. So in the SO10 gut, the only flavor symmetry, of course, rotates all the matter fields in this one multiplet together. So you just have one SU3, which acts on all of them simultaneously. So that was, of course, another possibility, this one here. Okay. How many more guts should I do? Does anybody know what Patti Salam is? Should we do We'll do Patti Salam, and then maybe we'll move on. OK, Patti Salam. Actually, maybe it's more interesting to do the example. Well, no, these are fast. Let's just do it. Patti Salam. So these are all guts that were written probably when you weren't born. This is more in the line of the general style of gut that I was talking about, where the gauge group isn't simple anymore. You just have no U1. Okay? So the Higgsing is that this goes to SU3C. This is untouched, and this is just, this is broken. At least this is unhiggsed. This is broken to diagonal. And one Cartan combination here gives you U1Y. OK, so if we look at this, this G Patti Salam that I wrote there going to SU3 color times SU2, left, you have the following 4, 2, 1. This easily goes to 3, 2, plus 1, 2, which is QL. And 4 bar 1, 2 goes to 3 bar 1 plus 3 bar 1 plus 1, 1 plus 1, 1, which is U bar, D bar, E bar, and we could say N. So that's another pattern that we hadn't realized yet, another entry in this table. OK, so by now you see kind of how this game is played. Now, before moving on, we might ask, are there examples that exploit this fact that I put in parentheses up there, the fact that the flavor symmetries are only approximate? There are some examples like that. I will briefly sketch one for you. So these would be kind of what, from this point of view, look like illegal unification patterns, but where I have extra matter that's suppressed by the Yukawa couplings, whose masses are suppressed by the Yukawa couplings. So I'll write one example like that for you. Any questions about these other kind of more standard examples?
In the George collection model, do we have U1 form symmetry is broken?
Yes. The one-form symmetry is broken in every one of these models. And all of those models predict dynamical monopoles also. More questions? No. People used to get tenure for this group theory. Okay, so.
By the way, excuse me. I remember parties along. You have a choice to model some Z2. So
yes, yes, yes.
Is the one of them one consumer? They may have a one consumer.
A discrete one. Yeah. I'm just talking about the continuous one in this talk. So what about Guts exploiting y not equal to 0? What does that actually look like in practice? So there's an example which is called trinification. What's trinification? Gtrin is 3 SU3s, hence the cute name. Sometimes people mod this out by a discrete group to try to force the gauge couplings to be equal. We don't need to do that. Okay. What are the matter multiplets in trinification? They come in 3. Again, the name is apt. So there's 3 bar 1. There's 3 bar 1 3. And there's 1 3 3 bar. Now, when we do the Higgsing to the standard model, we find something a little bit strange. So this has Q, but it also has somebody new, which I'll call D prime, a new down type quark. So this one here is in a 3 1. Somebody that we don't find up in the standard model list.
So how, given that everything is symmetric,
sorry?
Is there any subtlety about how the Higgs field, which breaks to the standard model gauge group, is chosen?
I mean, I have to choose a kind of funny representation to do it. I actually forget what the representation is, if that's the question. Okay, yeah. But actually, the Higgsing to the standard model is going to sort of, the fact that it's a little bit tricky is going to deliver the interesting effect here. So I'll show you that momentarily. But so the first thing is that when we do this Higgsing, we don't quite land just on the standard model content, or the standard model content plus neutrinos, plus right-handed plus singlets. We have, this should be D bar prime. This is in a 3 bar 1. We have an extra vector-like pair of down quarks. So this one doesn't give us anybody extra. So we have an extra vector-like pair of down quarks here. So we need to give them mass. Why do people think this is an okay unification if it doesn't quite seem to match the matter content of the standard model? Well, if you write down the Higgsing, so we have this extra vector-like down quarks. And if we, okay, now the UV Lagrangian, we have to have some Higgs field. And let me, with some foresight, write it like this. So this Higgs field is the one, this is our Higgs field. That is going to break us to the standard model gauge group. And when I do that, this interaction has a very nice thing that happens. So if lambda is the VEV of phi, it gives me a mass for the extra vector-like pair of down quarks. But it also, at the same time, is the one that produces some Yukawa couplings. So this is the pattern that I was trying to tell you was guaranteed to occur, which is that you can have here, and I should say, this is not a legal pattern of unification from this point of view, right? This Q is appearing on its own. So for instance, this model looks like it has a flavor symmetry that rotates just this. But I said that whenever that happens, it's precisely because the flavor symmetry is approximate, and that a manifestation of it will be that you will find extra matter fields whose masses are suppressed by the parameters that break the symmetry. So the point here is that the same Y that appears in the Yukawa matrices of the standard model and breaks the flavor symmetry necessarily also appears here. That this unique UV interaction ties them together.
Sorry, it should be D prime bar.
Sorry, yeah, thank you.
Hi, sorry, don't the gauge anomalies in the standard model particles cancel quite perfectly? When adding these two new quarks ruin that?
No, they're vector-like, right? From the viewpoint of the standard model, it's innocuous to add them. But we're getting actually kind of an interesting conclusion about them, that they have to be light by the same suppression scale. They're down from, usually you think that all the new physics of the gut is up near the Higgs scale. And I'm saying, no, that's not true. To the extent that you can think of the Yukawas as small, if you want to have this gut, you have to encounter light matter first.
Yes, strongly
with all due respect, this scale lambda is going to be astronomical. So y lambda, even though y is small, actually y lambda in practice is going to be very heavy, right?
It's very heavy, yeah. But it's much heavier than the gut scale.
Much heavier.
Or much lighter than the gut scale, yeah. Y lambda is much smaller than lambda. That's all I mean.
Well, it's not the model that Yukawa couplings for the one.
Yeah, but there are also small ones. There are also ones that are very small. So I'm doing it. So I'm doing kind of a simplified analysis where I'm treating the y's all uniform. If you want to do something more sophisticated, what you should do is do this analysis for the smallest y's individually and not talk about the whole SU3s.
I just wanted to point out that this, you're not making a prediction of some new particle which is easily experimentally accessible.
That's true. I mean, beyond the standard model physics is hard, yeah. Yeah. What?
Are they strongly interacting?
They're not strongly interacting.
They are green in color.
Yeah, but their mass is. I mean, it depends on what this is relative to the confinement scale. Yeah. Okay, more questions. Okay.
There's a question. I think.
Yeah, a comment. So
yeah, please.
It would be better to find a problem, not a confirmation, right?
Well, yeah, I agree with that. But the Georgia Glasgow model is consistent, so it's more like this is just a very, I think, a useful organizing principle for sort of how to think about all these different sort of wild possibilities. They're just, most of them are just entries on this list, just the consistent combinations on this list. Okay, any other questions, comments?
Did you try to come up with a new gut?
I did, yes.
And what happened?
I'm not very good at group theory.
But maybe this is a sign that something else is missing.
That's also true, yeah, it's also possible. Yeah. For instance, I don't think there is a known gut which does this possibility, if I'm correct. This is a possibility. That one would be interesting because it keeps all the quarks together, so it doesn't have proton decay at order 1. So that's a consistent possibility, but there is no known gut that has that. Okay. Any other questions? Okay, I have about half an hour left, I think.
Actually, I missed the point. The last black hole you write, you say the D and D prime, D prime and D prime are actual new particles, but why do you say that the Yukawa component is small?
I'm just saying that the mass scale for them is suppressed from the Higgsing scale by a power of the Yukawa. Yeah. Okay. I'd like to talk kind of quickly about a generalization of the ideas of these two lectures to models of axions. And most of the details I gave you, or a lot of the details I gave you as exercises. But this will be kind of variations on a theme. Okay, what's an axion? So we'll have a field A, which is a periodic scalar. Meaning that A is identified with A plus 2 pi f, where I'm in 4 space-time dimensions in these lectures, so f is a scale of mass dimension 1. This is not a symmetry, it's a redundancy. Okay. To start, S is just the free action. Okay, what are the symmetries of this free model? So currents, we have J mu, which is d mu A. This is a U1 zero form shift symmetry.
Clay, I have a simple question. Is f somehow integer valued?
No. F is scaling dimension 1, so it doesn't even make sense to ask. It's a mass scale. And then we have J mu nu rho. This is the new interesting beast in this example, which is epsilon mu nu rho lambda d lambda of A. This is a two-form symmetry. So this is probably the first interesting example that you have seen of a model with a two-form symmetry. Okay, I need my hook. Did anybody talk about axions yet? No. Okay. Okay, bye-bye standard model. It was nice while it lasted.
So the electron physics are not constrained by the table you just erased?
What?
Electron physics is not going to be constrained by the table you just erased.
I mean, people are interested in axions because they're realistic beyond the standard model ingredients. But before we do that, we won't have time to do that in these lectures. We should first warm up and learn what is the symmetry structure of axions to begin with.
I'm just trying to say maybe the thing you erase has something to do.
Indeed, yeah. Okay, coupling to gauge fields. People are interested in axions because they have natural couplings to gauge fields and might be relevant for, say, the strong CP problem. I'll talk about a baby version of that, where we can get everything very explicit. So we'll have a U1G dynamical gauge field. So we graduate from the free periodic scalar. Okay, so E here is the gauge coupling. So I should, again, emphasize, non-abelian versions of this are particularly interesting. So historically, one is interested in the case where A couples to SU3 color. But this is more explicit because it's U1 gauge field, so it will be easier for us to get our hands on. So E is the gauge coupling. K is another coupling. K specifies the strength at which the axion couples to the gauge field. And the claim is that K is quantized. So this is your first exercise in the homework problems that I assigned.
What is F?
F.
So little f.
Little f.
It's 8 pi square f.
F is that f. Right? So the axion, little f, the axion has as part of its definition a scale f. Right? That's built into the definition of what we meant by saying periodic scalar. And it appears here. And the reason I put it there is such that this quantization will come out to be literally integers. Okay, equations of motion.
So the periodicity of the scalar F also says on energy scale.
That's right. This model has some energy scale in it. And this, this coupling here, this is an irrelevant operator, right? Right? F has dimension 2, A has dimension 1. It's a canonically normalized scalar. So that's a dimension 5 operator, and it's suppressed by a scale, F. But that's the leading coupling between the axion and the gauge field, so we study it anyway. But you should think that this model needs some UV completion. Right? This is an effective field theory, and it needs some way of completing that term. Yeah.
So does the gauge coupling run here?
How does the gauge coupling run? This does very little to this does basically nothing to that because there's no directly charged particles.
It doesn't run.
Well, I guess it eventually would contribute, but it's not going to be like a one-loop beta function, yeah. But I can easily dress this model up by adding charge matter. I'm just sort of keeping it as minimal as possible right now.
So you mentioned a possible problem for UV completion for the model?
No, there's no problem. People know lots of UV completions of these axion-type models. That's a very well-studied subject. But I'm just saying that when I write an expression like this, it's got an irrelevant operator in it. So it's, you're going to have to eventually UV complete it. It's a good low-energy effective field theory, but you have to think about, eventually you'll have to confront the UV completion. The most famous is the KSVZ axion, where A in the UV is the phase of a scalar field. Okay, equations of motion. Okay, I will write the equations of motion in terms of the currents, because really we're interested in the symmetries. And just like Maxwell theory and the axion before it, the equations of motion are really just equations for the currents. So let's write them. D star J3, this is the 3-form current, so this is the conservation equation for that. That's still 0. So we still have the U1 2-form symmetry. D star J2, the magnetic one, is 0. So we still have the magnetic U1 1-form symmetry. Now it gets more interesting. D star J1. This is the 1-form current that is there in the axion because we had the shift symmetry. Now this is no longer 0. You can easily verify that this is k on 8 pi squared f wedge f.
And what's the notation? What's J3, J2, J1? What does this?
Sorry, it's the number of form indices. So this is that 3-form current there. I just got bored writing the indices and started writing it in terms of differential forms. Yeah. Okay, and then we have the last one, which is D star J2E. So this is the 2-form current that we had because of the electric symmetry, the electric 1-form symmetry. So this is like, d mu f mu nu up to some factors of couplings. This is also non-zero. This is minus k over 4 pi squared f. I hope I got the sign right since I'm writing it. dA wedge f. So, very nice. The equations of motion are all just equations for the would-be current. Remember when we had Maxwell theory on its own, not talking to an axion, we had these two exactly conserved 1-form symmetries. Now only one of them stayed exactly conserved.
Is J1 just a dA? What is J1 in terms of?
Yeah. So it's dA. Yeah. Yeah. It's up there. Yeah. J mu. If I put the indices on it, it's just the one that's conserved because A is free. Okay. So this implies various symmetry breakings. So what's the breaking? So the U1 0-form symmetry, that was the axion shift symmetry, is broken to zk0. And the U1 electric 1-form symmetry is broken to a zk 1-form electric symmetry. Remember, k is quantized. So for instance, the zk 0-form symmetry is a shift of the axion by 1 over k times its period. So a shift by the period is the nothing operation, because the period is a redundancy, but 1/kth of it is a symmetry, as long as that's a non-trivial symmetry if k is bigger than 1. And again, in the exercises that I gave you, you'll verify some of the fun parts of this statement. Because of this equation. You mean because we only have the field strength? No, but I mean, if I move A, it's because it's because A is not globally well defined. So like let's move this. So this term seems to, it's like a Chern-Simons term, right? Because A is bare here. And then so if you put the D here, now you have the naked A. And now shifting by a flat connection is not always going to work.
But actually, along those lines, can you play the same game that probably you'll tell us tomorrow, making it non-invertible?
You can do many non-invertible things. Yeah, people have done lots of non-invertible things, but I want to stick in the invertible world for today, and then then we'll do some non-invertible stuff tomorrow. Yeah, but pretending that we don't know about non-invertible symmetry, we continue here. So let's be in this case. Okay, so I'm almost out of time, and I just want to tell you a couple little things. So I want to tell you that there's a higher group here. We'll be in the situation k greater than 1, so that these statements will be non-trivial. In this case, it will be what you would call naturally a 3 group. This terminology is kind of tortured. By that, I just mean that the top part of the symmetry will be a 2-form symmetry as opposed to a 1-form symmetry. I'm sorry. How do you see it? Let me sketch a little bit how do you see it. So let's couple to backgrounds. Okay, so what will the backgrounds be? So there's a 3-form gauge field for this 2-form global symmetry. And there's also a 2-form gauge field for ZK 1-form symmetry. I'm going to isolate kind of the most interesting part of the higher group. There's lots of symmetry here, so there's lots of possible extensions to study. Right? We have 0-form, 1-form, and 2-form symmetry, so they can each be extended in sequence. But I'm going to isolate just these 2 parts. Okay, so if I want to couple to these background fields, so let's first discuss the coupling to this one. Okay, this is the easy one in a sense. I claim that this is I over 2 pi f integral dA wedge A3. I'm just writing there A mu J mu, but I wrote it in wedge product notation. Right? In this case, it's J with many indices. It's that J with 3 indices. And I'm contracting A with 3 indices upstairs with that J with 3 indices downstairs. But I just wrote it in wedge product notation, so we don't have to write as many indices. Okay, so that one is not so bad. So that's the first part. How do you figure out how to couple to this? Max kind of already said the answer just a moment ago. How do you couple to B2? So we use the fact that the photon is a Goldstone. That's a physical way of saying the mathematical fact that the dynamical field, which is the connection here, shifts under the symmetry. So what that means is that we just take F, and wherever we see big F in the action, we replace it by F minus B. That's how to get the coupling to B. So that means that our action will contain another term which looks like this. I'm again going to look at the most interesting term. What should you notice about this? What should you notice is that it corrects the coupling to little a by something nonlinear in B. So it implies, in particular, that the gauge invariant field strength of A3 is not just dA3, but we can call it G4, which is dA3 plus k over 4 pi B2 wedge B2. I'm reading this off from the thing that couples linearly to dA, taking into account various quantization conditions to remove an FB term. So I hope that you saw enough of these kind of field strengths and gauge transformations in Thomas's lecture to recognize that this implies a higher group. When you have a gauge invariant field strength that includes the linear term plus a correction by a lower degree term, that's the higher group. That's the signal. All right, so the bat signal is up. So the quadratic term implies a higher group. So we have this U12 extending ZK1. And now the last thing I want to tell you is that just like before, we can apply an emergence theorem in this context. Right? We have a quotient and an extent and a subgroup, and the quotient is not a subgroup. So we get a similar kind of emergence theorem. So this is a very general logic whenever you have this kind of higher group structure. So you consider a UV and an RG flow to an IR. Here you have G, and here G is broken. And E2 and E1 are the scales of emergence of the 2-form and 1-form symmetry. And we get this kind of inequality. Now, again, you might ask, what more physically is this? E1 is like the scale of charged particles. Right? For instance, if we had an electron, it would break E1. It would break the 1-form symmetry, electron of charge 1. And E2, that's the scale of dynamical axion strings. So just as before, we get general constraints on UV completions of axion models about how the charged particles and the strings must arrange themselves. And of course, if you now go look at explicit UV completions that people have written down, you will find that they obey this general argument. OK, so I'll stop here. Thanks very much.